So I'm going to talk to you guys today about the group that I belong to. It's called the Bighorn Basin Paleontological Institute. I'm going to talk about that. I'm going to talk about the geology of where we do our research and a little bit about how paleontologists choose where to go digging. I'm going to talk to you guys about the process of finding the fossils, bringing them out of the field, and doing some research. And hopefully you'll enjoy us as we go along. So this first image, this hunting dinosaur image, you can see a long-tailed dinosaur here. It's called sauropod called Suawasia. And it is one of the dinosaurs that we have been excavating at our field sites. This painting was done by our field site coordinator, Jason Poole. He is also a paleo artist. So, where do we go and why? This is an image of the field site that we stay at out in Montana. It's called the Yellowstone Bighorn Research Association. And it was founded in 1936 as a place for geologists and paleontologists to have a field site so that we could have a great place to stay and go back in the evenings before we go out to dig. And why is it located here? It's about an hour west of Billings, Montana, and it's right on the edge of something called the Bighorn Basin. And I'm going to talk to you a little bit about the geology of that in a second. But I did want to mention that this beautiful site, we're very lucky to have it, to be there, but it was almost destroyed this year due to the fires that are out in Montana and Wyoming. Our fire seasons are getting earlier and more intense. Climate change is something that paleontologists study. We study climate and how it changes over time and over millions and millions of years to try to understand impacts that we might see today from climate change. But it became really more immediate this year because the mountain that we stay on, where this camp is located, is called Mount Maurice, and it actually is on fire as we speak. There were 2 times during the summer where the fire line came right up to the edge of the camp, and only due to a change of wind was the camp saved. So climate change does actually has even a more immediate effect even on us today. The fire as of today is about 90% contained. The firefighters are active and stay on the mountain and put down flares. We actually this summer, while the week I was out there, had to pack go bags one night because we came back out of the field. The mountain was on fire again, and we had to be prepared to evacuate. So the firemen out there, they're heroes. All firemen are, but it was just really impactful. We need a big snow season this winter to put the rest of the fire out. So somebody was telling me about it says they smoke spread as far as Utah from some of the fires. Actually, interestingly enough, while I was out in the Bighorn Basin this summer, our RV air quality volunteer project that we're running here at the museum, we're picking up smoke from the fires out in Oregon and California, Montana. It made it all the way to the East Coast. So that's how intense the fire season has been out there this year. So YBRA is where we stay. And the reason we stay there is because it's right on the edge of the Bighorn Basin. This map that you're seeing here, the basin itself is about 100 miles north to south and about 60 miles east to west. That red star is where our field sites are, and our camp's a little bit north and west of there. It's surrounded by several mountain ranges, which I'm going to tell you a little bit more about in a second. But the Beartooth Mountains, which are over to the left of that star, one of the cool things about the Beartooth Mountains is it has the highest point in Montana. It's about 12,000 feet above sea level, and going over across the side of that mountain is Yellowstone. So we're about 2 hours from Yellowstone in this mountain and basin area. just another image of the different mountains, the Beartooth Range, the Absarokas, the Pryors, the Bighorns, Owl Creek, and the Bridger. And they're surrounding this entire flat basin. Now, the basin's still pretty high up. It's about 4,000 feet above sea level. Just to let you know the comparison from there, Richmond's about at 166 feet above sea level. So it's very high up. We do have to adjust for climate change. I mean, not climate change, for altitude change. Even though it is a desert, it's still really high. And so the first day or two in camp, a lot of folks who aren't used to the altitude can experience altitude sickness. So how did it form? So if we go back here for a second, the basin within these mountains, what's happened is, if you can imagine a tablecloth, and that you're pushing the tablecloth or a blanket across your bed. And as the blanket starts to compress, you get a series of up and down dips, kind of like a wave formation. And that's what's happening to the continent right there. The formation of these mountains, the Beartooths, the Absarokas, what happened was about 67 to 64 million years ago, there was a mountain building event that started to push the continental crust just like you would that tablecloth across the table. And it created a series of basins and ranges. And in fact, the easternmost end of that basin and range formation makes it all the way to the Black Hills in South Dakota. So it's a huge squishing of the continental crust. And as it did that, the older rocks of the mountains, like the Beartooths, which the rocks in the Beartooths are igneous and metamorphic, and they're 3 billion years old, were lifted up into the ranges, and then the basins formed in between them. And so there's a whole series, of which the Bighorn Basin is just one. And if you look at the lower image here where it says Bighorn Basin, that light green colored rock is the sediments that we're actually digging in. So there's these older billions of year olds continental rock that, and then over time they started to fill in with additional sediments. One of the fun things about this is that the sites that we're digging are squarely in the Jurassic and the Cretaceous. So somewhere between 156 million years old and 66 million years old. But because of the way the basin formed and the uplift of the rocks that are older than the sediments we're digging, which is unusual, right? Because normally one of the key rules of geology is the law of superposition, where the oldest things are at the bottom and younger sediments are on top, which is how sediments are deposited, right? You're making a cake, the oldest layer would be the first one in the pan, then the next layer would be younger than the one you first put into your cake pan. But because of that basin and range formation and that squishing, some of the older rocks got lifted above younger rocks and they erode down into our sites. And what you see in my hand right here are actually some fossils of belemnites, which are an extinct cephalopod, and extinct clams that we sometimes find scattered throughout our sites, but are actually older than the dinosaurs we're looking for. And we get to keep these fossils. You are not allowed to keep vertebrate fossils like the dinosaurs. We dig on government property. We dig on BLM land, which is Bureau of Land Management. We have to have a permit to be out there. And all vertebrate fossils, like dinosaurs, have to go back to a museum. Nobody can just go pick one up and take it home with them. But invertebrate fossils, for what it's worth, and plant fossils like petrified wood, you're allowed to take up to, I can't remember the poundage, but a certain amount of poundage you're allowed to take. So I definitely have some of these in my home. The site that we're at, again, is the Red Star. And in the Jurassic sites that we dig, in the last couple of years, not counting the COVID year, because we didn't go out last year, as many of us were impacted by the pandemic, 156 million years ago, when our dinosaurs were wandering around where that Red Star is, you can see there was an inland sea. So this is called the Western Interior Seaway. And from the late Jurassic into the Cretaceous, this was at varying times a very large body of salt water. In the Jurassic, as you can see here, it ended in Montana and Wyoming in that area. By the late Cretaceous, this waterway went all the way from Canada all the way into the Gulf of Mexico. And the environment was very similar to what we see in New Orleans and Louisiana today. There were bayous, there were moving rivers, it was subtropical, and it was a really great place for deposition, for the formation of fossils, because of that water putting sediments over anything that might have died. This image is looking south into the basin. So that basin we talked about, the Bighorn Basin, this is just the tip of it in Montana. And what you're looking at right here, which just looks like open, beautiful open country with a road going through it, used to be towns and coal mines. This is one of the most productive coal, oil, and natural gas fields, or used to be, in North America. Right after the time of the dinosaurs, the area became even more swampy and layers of coal were laid down. And for years, this was mined until about 100 years ago. And when the mines closed down, all the towns disappeared. So this all used to be occupied, which I find fascinating. Another place along our Bighorn Basin where we go hits the Cretaceous Paleogene boundary. And I thought I'd show you this image. Is our sites within the basin, as I said, go from Jurassic through to Cretaceous. It was deposited for a very long time along the Western Interior Seaway. And on the road to one of our Cretaceous sites, we pass an exposure of the boundary where the asteroid hit. That is very famous for hitting in the Gulf of Mexico, that caused the extinction of a large amount of life on Earth, including the non-bird dinosaurs. And where I'm sitting and pointing to right here is a relatively thick layer right immediately above the Cretaceous Paleogene boundary at 66 million years ago that shows is carbonized. So there were massive amounts of fires that took place across the planet after the asteroid hit, and it's exposed right here. And I actually have a small sample of this carbonized forest, basically, that burned at the museum that we can use this to teach with. So if you want to see a piece of the Cretaceous Paleogene boundary, come visit us. So how do we know where to go in the basin? How do paleontologists know where to go at all? Well, one of the things is that you have to know the right age of rocks. Fossils, we have fossils on the planet dating back a little about around 3.5 billion years. The first fossils of life show up in that age of rocks, and they're single-celled organisms like bacteria. They have to be sedimentary rocks. You very rarely find rock fossils in anything else. There's some weird exceptions to that, but you need a depositional sedimentary rock that haven't been melted, they haven't been metamorphized. So you have to have sedimentary rocks. They have to be exposed. So there's sedimentary rocks of the right age of the dinosaurs everywhere, but they could be under a mountain. They could be under 20,000 other feet of sediment. They could be under a forest. They could be under a shopping mall. So not everywhere on the planet that might have the right age rocks is accessible. So that's another key factor. So one of the reasons you see paleontologists so often, if you watch TV shows or things like that, they're in deserts, because deserts have a lot of erosion and exposed rocks. So the Bighorn Basin is a desert. It's a high-level plateau desert, but it's still a desert. It's very dry. It's got lots of layers. You can actually see the layers, and you can see them a little bit in this image, heading down into one of our sites. Along the top of that ridge in the middle of the image, you can see different rock outcrops. And we geologists have mapped those rock outcrops, and you can literally go back in time as you go down them and target the right age rocks that you're looking for. Takes us about an hour to 2 hours to get to our site, depending on where it is. You can see us here getting out of our Suburbans, getting ready for our first day out in the field. And one thing I'm going to tell you also about these sites is that because they're BLM land, like I said, and they belong to all of us, right? It's government owned land, which means your tax dollars at work are preserving this land for groups like us. We are not allowed to take pictures that show both fossils and horizon in them, because there are people that will come out and literally follow groups like ours to poach fossils. It's kind of scary in some ways. Every year the BLM will give us, there are people that they know about, they'll give us truck descriptions, face descriptions if they know about it, so that we can keep an eye out and make sure that people aren't following us out there. So we're always really careful to take out any geolocating devices from our pictures. So like if we're going to post something on social media, we don't have it geotagged because people will find that. And we try not to have anything that has fossils and horizon in it, just so that they can't co-locate it. It's not perfect, but we do try to be really careful. I see another question that said, have you ever been followed by bandits before? And if so, what did you do about it? There have been a couple of summers where like we haven't actually seen them, but that there were some known poachers that the BLM was very spent a lot of time with the directors of the program, and were checking in with us every week just to see if we'd seen anybody, and they had targeted trucks that they wanted folks to look out for. Not as much this past summer, but we've definitely had some summers where they were very active. And I see another question that says, can I find a dinosaur bone in my backyard? And it really depends on your backyard. If your backyard is in a place where you have the right age rocks, like if your backyard is Montana, it's very highly, it could be likely. There are stories of people finding fossils, not always of dinosaurs, of other animals in their backyards. In Virginia, it's probably rare. It'd be very unlikely at the moment in Virginia, although there's always a first one. The only fossils in Virginia we have of dinosaurs are some footprints. Very few of the rocks in Virginia are from the Mesozoic, the time of the dinosaurs. There's very few. There are a few sites, though, in Virginia that we're very hopeful that someday might reveal an actual body fossil of a dinosaur beyond footprints. We actually have a really cool digital interactive at the museum right now that has a list of all, walks you through the fossils that you can find in Virginia. So you may not find a dinosaur, but there are definitely other species of fossils from other time periods that Virginia is known for, like whales and sharks. So somebody said, have you ever found crocodilians in the Bighorn dig site? There are areas in the Cretaceous places that we dig, because this was in the Cretaceous areas, because it was even more of that inland sea, so that marshy environment. We do find, in conjunction with where we find the dinosaur fossils, because it was the dinosaur would have died alongside the ocean or the seaway and then got covered by ocean sediments. We will find crocodilians and turtle pieces. We'll find crocodile scutes and turtle pieces of turtle shell and crocodile teeth in association with the dinosaurs in the Cretaceous sites. So the fossils don't necessarily like have little signs on them like, here I'm sitting here. You watch movies like Jurassic Park, which I love, but they seem really easy to find in those types of movies. But once you find the right age rocks and you can get to them and they're exposed, you do a lot of what we're doing in this picture here, which is called prospecting. You walk around and you look at the ground. And what you're looking for are little pieces of fossil that might have eroded off a more full specimen over the winter. And you have to practice getting a search image for that. You do also have to look out for wildlife. just because it's a desert doesn't mean there aren't critters out there. And you can see some of the things that we deal with. Some are cute, like the horned toad in my hand. It's a lizard, not a toad. Jackrabbits. We have coyotes. We have elk and deer. We also have scorpions, which are often under many rocks. And even near where my current site is, called Rattlesnake Ridge, you do have to be careful while you're out there. So in this image right here, I'll give you a second. I said as we're prospecting, we're looking for little pieces of dinosaur fossil float, and I have a piece in my hand. And in this image, there's a whole bunch of rocks, of which a handful of them are actually fossils. And in this instance, they happen to be the ones that are lighter colored right in the center. And it doesn't take too long to get a search image and go like, oh, that's a fossil. Ooh, that's a fossil. But it's always better to pick it up and be wrong than it is to leave behind something that might be actually lead you to a new find. Another really cool thing about prospecting and dinosaur fossils, when you're looking for the body fossils, they originally were bone. And bone is very porous. There's lots of teeny tiny holes in it. And even the fossilized bone, even though it's no longer mostly bone, it's now a mineralized, still has those tiny little pores. And if you pick it up and you stick it to your tongue and you put it on your tongue, if it is a fossil, it will stick. And because of capillary action. And it's really cool. So you'll see a lot of us out there licking the rocks that we find. And if it sticks, it's probably a fossil. Once you find the float, what you do is you follow it back up to where its source is. And hopefully what you find is a more complete fossil. And the images you see here was some pictures from this season. We found what hopefully will be a site for next year. In my hand on the left side of your screen is what looks like a round rock. And what it actually is, which is so cool because you hardly ever find these, is the occipital condyle. It's the piece of the vertebrae that attaches to the back of the skull of a sauropod. It's one of the only round bones in the animal's entire body. And it is just such a cool find. And on the right hand side, you see us we're finding more of this. This was a pretty big pieces of this sauropod. We got a couple of vertebrae. We've got what looks like piece of a toe bone. So we've GPSed it, we've marked it, and next year we hope we'll open up a bigger site. Where we are in the Jurassic area also sometimes is one of the reasons we love this site. It's huge. And you can't shake a stick without finding a fossil. Sometimes you find a site and it's really hard to find a fossil. Other times you get out of the car for the day and there's a fossil at your foot. And that's what I'm holding here. I'm holding the toe bone of an Allosaurus, which is a meat-eating dinosaur. And it was literally under my foot when I got out of the car for that morning of digging, which is just awesome. And where we're pointing with the fingers in the other picture, this was just a really cool random fossil find. We didn't find the rest of this Allosaurus, but there are bite marks on this fossil where another Allosaur was chewing on it. So, I mean, like, it's just immediate, the things that you can learn while you're out there. So what does it take to get the fossils out once you find them? On the right-hand side of the picture is one of our quarries, we call them, from this year. It's our LZ Blue quarry. It has been a very productive quarry. You see, we've got shovels and we've got brushes. We've got flathead screwdrivers, which are surprisingly useful for digging out dinosaurs as you're slowly chiseling the rock away. This quarry's produced at least 5 different species of dinosaur right on top of each other. Mostly sauropods, those long-necked dinosaurs, little bits and pieces of them. We're not exactly sure what happened here. We're trying to understand how they all got there, which is a process called taphonomy. So this one's pretty flat, and right now we're just trying to widen the quarry, and then as we find fossil, protect it and get it out. And I'll tell you a little bit about that in a second. On the left-hand side of the picture is one of our Cretaceous sites, and that hill you see, we found a dinosaur fossil on top of that. That was a lot harder to get the dinosaur out of. After we mapped it, so you can see Jason here in actually both of the people in these images are named Jason. We have 2 Jasons on the team, are gridding and mapping and drawing the fossils in place before we take them out. Again, that helps us remember when we get them back to the museum, how to put them back together, how they were found, because how they were found can help us understand how it died and how it got there, which is really important, understanding the ecology. So they are mapping that here. Once we do that, we can take the fossils out. And that hill I showed you before, I'll go back a second. Here it is, it all in one piece. And then that's what we had to remove to get out a very small piece of the front rostrum or nose of a Triceratops. So we had to climb up this hill with all of our gear, with a jackhammer, with water and plaster to get this out of some of the hardest rock I have ever seen. And you can see there's 100% no shade. It was brutal. But it was a really fascinating experience, but boy, it was brutal. And then to get it out of that site is about a mile hike from the cars. So we also had to hike that out. So you try to get in this image is the rib of a Diplodocus. Some of us trying with our screwdrivers and our awls, getting it out. You don't want to perfectly get the fossil out. What you want to do is to get it out with some surrounding rock. And so all of that rock that you see surrounding what is the rib will get taken back with us. You want to protect it on its way back to whatever museum it's going to, so it doesn't break anymore. You know, they're fragmented, they need to be protected. So you take out a lot of the surrounding rock with it. It's called pedestaling. These are just some more images. Sometimes there's little fragments. The top picture is some Allosaurus teeth that we got out. We got a pretty complete Allosaur 2 years ago. And the bottom picture, it's a little blurry, but is the tail end very nicely articulated, which doesn't always happen, of that Suawasia, that dinosaur from my very first picture. We found a lot of it. We're actually still trying to get it out 3 years later. So one of the first, once you get it pedestaled, you're going to jacket the top, which requires mixing a lot of plaster, which is what you see us doing in this video here. So we want it to be about as thick as pancake batter, and then we'll start dipping burlap in it. And you see, and that burlap then goes on top of your fossil, which you can see us doing in the top picture here. It's been top jacketed. Now, you don't want the plaster to touch the fossil. That's really important. So we'll cover the fossil with layers of tinfoil, wet toilet paper, and paper towels before we put the plaster and burlap on, because just to make sure that the burlap and the plaster doesn't adhere to the fossil, so that when we get it back to the laboratory, we're not also trying to take plaster off in addition to the rock. Once that dries and sets, you then, which can take a day to 3 or 4 days, depending on whether you mix the plaster right or what the temperature is. But once you do that, then, so you can see us, more of us top jacketing a fossil that we were getting out, then you have to flip it. Sometimes they can be really big. In the left-hand picture is that tail of Suawasia again, and these are, 500 to 1,000 pound jackets. And then in the right-hand picture is the hip bones of a stegosaur from 2 years ago. And the young woman that you can see lying down next to it, that's my a friend of mine, and she's about 5 feet tall. So you can see just how big the side of that jacket is. So you can imagine, like, okay, now what? How do we flip something that's up to 2,000 pounds? Well, this is us just after we jacketed. You get very, very, very dirty. But so this is us flipping that Stegosaurus jacket. So we've got a whole bunch of people and a lot of ropes. We've got it tied to a car. We've got a wooden platform on the back, and then we're trying to pull it. You can see. And then Rick jumping out of the way. And so we got it flipped. And then what we do is we go in and we put a jacket on the other side. Let that dry. And then hopefully it's not so heavy that we can't get it out of the field. One of this site that you see them flipping the jacket here is really near a sandstone mine. And the miners have been really awesome to us, and they have huge equipment, and the last couple of years they've been awesome, and they've come out with their gigantic equipment and lifted the fossils up onto the flatbeds of the trailers that we use to drive the fossils back out of the field. And they've been really nice about it and geeked out about it, right? Because they're like, what, you're digging dinosaurs? So they've been really nice. However, we can't always get the whole dinosaur out each year. The two women you see here are two of our preparators and field agents. And hopefully at the end of a season, if anything that you can't get, you've covered with a jacket, and then we rebury it before we leave. If we can't bring it out of the field, we cover it with tarps and we cover it back with soil. Two reasons. One, we want to protect it because even though it's a desert, the winters are harsh. The other reason is we don't want people to find it. Right? We've got those people that we're worried about coming out and stealing things. So we don't want big giant holes in the ground. So we bury it back up. So when you got the next season, you dig it back up, and you hopefully everything that you've done to protect the fossil stayed together. Well, because of COVID, we had 2 winters before we could get back out to this particular site. And some of the jackets basically fell apart. They just didn't make it through 2 winters. So what we did this summer is we opened those jackets up and started taking the fossils carefully out of them so that we were making smaller jackets so we could get them out this year. You don't want to do that. That's not an ideal situation, but working through the pandemic, we had to do what we had to do. Then at the end of the season, which is normally around the 3rd week of August, we close up the site. We pack everything up that we are going to bring back out with us, and the team brings the fossils back out to the East Coast. The fossils are not prepared out in the field. You go to a dinosaur exhibit in a museum like the one we have up right now. They are not prepared in the field. They're prepared in a lab at a museum. So the fossils that the Bighorn Basin Paleontological Institute goes to 2 different museums. They go to the Academy of Natural Sciences in Philadelphia for their paleo prep lab, and they go to the Cleveland Museum of Natural History, it's the Cincinnati Museum of Natural History. So they go, and then they're permanently stored in those 2 locations. Again, and digging on public land, they have to go to an accredited museum, which I think is pretty cool. And it can take years to finish opening the jackets, preparing the fossils for study and research, which is another part of the story. I'm going to stop here. I see a couple more questions, and then I'll also see if Jim gets any that I haven't seen. So I see one from earlier that talks about carbon dating, which is a good question. Dinosaurs are too old for carbon dating. Carbon dating is a way of using, for those of you who may not be familiar with it, using radioactive isotopes of carbon to date a fossil or an archaeological dig. Carbon, radioactive isotopes of carbon decay at a certain rate, and then you can measure how long it's been decaying to get an idea of how old it is. Carbon dating, though, radiometric isotopes of carbon only get you about 60,000 years old. Carbon decays relatively rapidly. To date things like dinosaurs or things earlier than dinosaurs, like the rocks in the Beartooth Mountains, which are 3 billion years old, you have to use different radioactive isotopes, things like uranium and things like that. So that you have things with longer decay periods so you can get back older times. Other thing, though, is that you can't normally date the sedimentary rocks directly. You normally have to date something like a volcanic rock, which would have the radioactive isotope in it that So that might sandwich the rocks you're interested in. So there might have been a volcanic lava flow at 200 million years ago, and maybe another one at 155 million years ago. And then there's several layers of sedimentary rock in between. And you date the upper and lower ones, so you can get a range of where your dinosaurs are. So you get as specific as you can in the range, and then you do it by what's older or younger, above and below. I see another question: where can my family go hunt for dinosaur fossils? Well, interestingly enough, there are a lot of groups that take group people out. In fact, the Bighorn Basin Paleontological Institute, the group that I'm showing you pictures of from here, our whole mission is to give people an opportunity to do citizen science and be a part of the digging dinosaur process. People can sign up to spend a week with us, 2 weeks, 3 weeks, 6 weeks, it's up to you, and spend their vacation with us digging dinosaurs. So people come out, and most people spend a week to 2 weeks. And during the day we go out and dig dinosaurs. The night we do classes for the guests and all sorts of other things. We also do day trips. People who are traveling out west to go to Yellowstone or see other sites in the Midwest will spend a day with us digging dinosaurs. And that's how we get the help we need to do all this massive amount of work. The team itself, the people who are permanently part of the team, there's only about 6 of them. And that's not nearly enough people to help the dinosaurs out. So that is why we exist, is to get people to come out with us. You have to be 13 and above to come out, but it's definitely a really fun way to participate in science. How did dinosaurs go extinct? Do dinosaurs exist today? Yes, they do. Birds are dinosaurs, which could be a talk on its own. But one group of dinosaurs evolved into the birds we know today. So chickens, the hummingbirds, and everything in between are dinosaurs. And the birds survived the extinction from when the asteroid hit about 66 million years ago. The asteroid was probably part of a 1-2 punch. There are other significant geological events that happened towards the end of the Cretaceous, including massive lava flows in what is now India, continent-sized lava flows right near the end of the Cretaceous. And then when that asteroid hit, pretty much wiped out anything that was, larger than a coyote, including things in the ocean. But birds and things that were able to bury or take shelter made it through. What is the biggest carnivore I've ever found? The biggest carnivore I've ever found from the sites we've gone in, I can answer that in a couple different ways. The most complete would be that Allosaurus I showed you the teeth of. We got a lot of that Allosaurus. The only thing that was missing was the tail end. Got a lot of the front limbs, some of the lower limbs, and almost a complete skull. Although the skull was shattered, which was really interesting. It looked like it had swallowed a hand grenade, just in so many pieces. The largest type of carnivore I've ever gotten to help find was, we found the limb bone of a Tyrannosaurus Rex at one of our Cretaceous sites, but it was only the limb bone. We found nothing else of the animal. So T-Rex was the largest land carnivore to ever live. So I guess I could say I've helped find a T-Rex, but it was just a leg. How many different species of dinosaurs have I found? Well, the team itself, I think, over the course of the Bighorn Basin has been around for a number of years. And I would say we've probably excavated pieces of, off the top of my head, probably at least 15 different species of dinosaur, probably closer to 20. The most interesting fossil, well, finding that occipital condyle this year was pretty cool. We've also found at one of our sites called the Mother's Day site. It's a fascinating site. It's been excavated for a long time, not just by our team. And the only species of dinosaur that has ever been found in that site are Diplodocus. It's a long-necked dinosaur. And it's hundreds of specimens of very small Diplodocus. None of them are adult-sized animals. So it's kind of a fascinating site. So why are they only juveniles? Why are they only small? So is it because they were in a herd where all the small ones were hanging out together like some animals do today, where the young stayed together for safety and they got washed away in a flood event? Is it an island situation where they're dwarves? It's well known from studying modern animals and modern islands that islands often cause species to either grow really, really big or big species to go really, really small. So is this an example where Diplodocus, which is a very large dinosaur, usually was on an island type habitat and they shrunk over millions of years and became a smaller dwarf sized population? Those are both testable hypotheses that we hope to do. It's more likely that they're juveniles, and you can tell that by their bone patterns, whether the bones have fused, just like on humans. As they got older, bones would fuse versus having open pieces when they're young. But it's such a fascinating site, and it's just tons and tons and tons of layers and layers of Diplodocus material. We've also got skin impressions from that site, from where the Diplodocus, when it died and got covered really rapidly with sediment. We actually have skin patterns in the fossils. We've put out some papers on that, which is really cool. What else do I see? It's probably the weirdest. So like, I don't know about weird. Like, I think like unusual would be those the Diplodocus finds. I think that's really that's been a really fascinating story. Oh, somebody wanted to say that Spinosaurus is bigger than T-Rex. I guess this depends. I won't argue with that. I think it just depends on your definition of big. They're definitely Spinosaurus is longer than T-Rex. Wasn't heavier, so it just depends. They were both very large animals and very good at eating things. So they're both really amazingly cool dinosaurs. One of the people that I work with on this dig, Jason Poole, the artist, and also the site manager, has had the ability, I don't know, that's not the word I'm looking for. He's had the pleasure of going on a dig in North Africa. In fact, if you ever want to read the book called Lost Dinosaurs of Egypt, he's one of the paleontologists featured in that book. And they went back to Egypt to look for new specimens of Spinosaurus. And this was a number of years ago. And so now, of course, we found multiple new specimens of Spinosaurus. And he got to be out there and part of one of those expeditions looking for new Spinosaurus. And the one he went in, they didn't find Spinosaurus, but they did find a couple new species of dinosaur, which I think is pretty cool. Oh, somebody else asked, will dinosaurs come back? Well, birds are still here. So, you mean, or do you mean like our exhibit? I would always love to have more dinosaurs because they're a passion of mine. But next summer, sharks, which are also cool and also have cool fossils. So how do we account for the very rapid growth of T-Rex, as even Scotty was only about 30 years old? Oh, the Scotty is the very large T-Rex in our exhibit. And I think this might be my last question. And in case if you're not reading the chat, because I know there's some Spinosaurus lovers on this call. It says, if you love Spinosaurus, check out our earlier Lunch Break Science. Dr. David Hone, who's a really cool paleontologist, did an amazing talk on all the recent paleontology of Spinosaurus. It was a fabulous talk, and you can find it on our YouTube channel and our Lunch Break Science. And it was only a month or so ago. All right, so my last question is the rapid age of growth with Tyrannosaurs. Tyrannosaurs are one of the animals that grew up fast, lived short little lives, and died young by our standards. But other animals on the planet don't necessarily live their lifespans like humans do. There are animals that spend their whole lives as juveniles and only live one day as adults. Think of like a mayfly. And tyrannosaurs are in an interesting situation where it seems like once they hatched, they grew up really rapidly and reached adult size by their late teens. And the oldest specimens we have of any tyrannosaurs seem to only be about in their 30s when they died, and they were old by then, if you will. And we're not exactly sure why this happened, like what was with that rapid growth, but we can tell that this happened by looking at cross sections of their fossils under microscopes, because your bones make different growth patterns as you grow, and they do put down rings in a way very similar to a tree does, especially in reptiles. And so you can take really thin slices of their bones and look at them and look at where they were being laid down rapidly or when that sloth growed down. And that's how we've generated growth growth curves for the Tyrannosaur fossils that we have. We've really enjoyed having you here today. And thank you for continuing to stay with us virtually for Lunch Break Science. Jim?
All right, Timshel, thanks so much. So the month of September, we have got some great speakers lined up for all things dinosaur related. So definitely do watch this space for the month of September. We've got some great ones to wrap up the run of Tyrannosaurus Meets Family. So next Wednesday, September 1st, we have got Adventures in Ancient Africa on the Trail of the Origin of Dinosaurs, and that's going to be presented by Dr. Sterling Nesbitt, Associate Professor at Virginia Tech. As you can register for next week's talk at smb.org. Each talk is free to attend and is open to the first 300 registrants. Thank you all for joining us today. Thank you, Timshel, my friend, my favorite dinosaur hunter. And until next week, stay safe and stay curious.